Hi everyone, welcome to CET3198. In this brief video, I'm going to be reviewing the homework number 4. We want to start with the first problem in which we are given 8-1 mocks in which the inputs are connected either with 1 or 0. And then we're doing this to generate a function f. And then we would like to know what function is implemented. So the best way is to build the truth table or the K-map, even better, because basically both are the same thing. And well, this is the K-map or the truth table for this function. So remember, for instance, the way you do it is that use the selection inputs A, B, and C to you start changing that. Okay, so for instance, when you have A0, B0, C0, this is the input that you're going to have. So we provide all the possible values or combinations for A, B, and C, and then we look here in the input to see what exactly is that. So we find that this is the K-map or the truth table, and then we look into the mean terms here, right? And then we have the 0, the 1, the mean term 4, mean term 6, and mean term 7. So this is part of the solution. But see that we're given a couple more of options. For instance, in terms of the max terms. So if I'm giving the mean terms, I can get the max term by difference. So all the elements that are not here in the mean terms are max terms, and then this is exactly the max term that are derived from here. So we have the 2, 3, 5. So both the A and D are correct. So remember, this is always like that always. Don't you find a solution? Okay, don't stay there. You need to go further and see if the other solutions are also valid. Okay, by now you should be current in that. The second question is also the same approach. You have a connection of two multiplexer and cascade. One is a 2-to-1 and the other one is 4-to-1. And then this is the table to check the condition. So for instance, in this case, we know that A0 allows this path, the upper, to go through Y. And here we have a ground connected to this port, to 1. So we know that no matter what, once we have A equals 1, we're going to have this element 0. Okay, so this forces a 0 every time A is 1. Okay, so all we need to do is just go by one. We start with 0, so that's the upper element here. And then we notice that for the B and C 0, 0, 1, 0, we're going to have a 0 because the input is ground. So that means that we have a 0 input here. Whereas with 0, 1, and 1, 1, we have a BCC. So we start doing the same thing as the problem 1. We start changing this and see what input is allocated to go through the output. And then we build our kernel mapped or truth table. So we have here that, as I said, A0 means all of these 0. And then we have a 1 here and another 1 here that corresponds to whenever we have a 0, 1 and 1, 1 in B and C. Okay, See the location for that. Okay, so with that, then we can have easily get the expression, because in this case we're getting the expression for y, and clearly you can see that this is not A and C. Okay. All right. Let's see with question 3. Still another one, similar approach. There's a multiplexer to implement functions, and we have pretty much the same situation. The only thing is that a difference with the past two examples, that we have only inputs tied to either VCC or ground. In this case, we're using an extra variable as an input. That means that we have 3 inputs here, 3 variables, A, B, and C, and then it's a 4th variable that changes, and then it basically the changes in this input will change the output in here. So it is a 4 variable functions that we're getting from there. All right. See that the approach again is exactly the same thing. We're start looking into changing the inputs, the selector gates, and then we see for each one of the inputs what exactly we have here. This is a K-map for the 4 inputs or 4 variable function. Here is a particular interest in the typical the H1 multiplexer that we use to implement 4 variable functions. See, it's a very straightforward approach. See, you divide the K-map into 8 different sections. If you look into what is each one of the sections, for instance, in this case, we have this rectangle in red. That rectangle in red corresponds to the inputs A0, B0, C0, right? A0, B0, and C0. And what exactly is the input here? Well, it's D. Therefore, we look into here, into value of D. In this case, D is 0, so the value will be 0. And in here, the value is 1, so the value here would be 1. Similarly, with the rest of the K-map, see, for instance, let's see the case in which we have 0, 0, 1, right? Which is 0, 0, 1 would be the I1 input. In this case, I1 is tied to ground, so both of them are 0. There's no chance to have a 1 or anything different to 0 here because they are tied to the ground. Okay? In the case of I2, that would be in this case because we have A1, A0, B1, and C0. That's a true. And C, in this case, we have VCC. So no matter what, the changes of A or here, D, I'm sorry, there's no change in here. It will be tied to VCC. So you keep doing exactly the same thing. In this case, if you look into the cover for that function, okay, we can use this cover of 4. I have another here and another of 2 variables. Okay, so this answer, let me see which one is to be sure. So we have, in this case, we have this implicant here is is B and C naught. Okay, B and C naught. This one, this rectangle here, is not C D, not CD. And this one is here is A, B, that correspond to this column, and then C. Okay? No, sorry. That will correspond to A, B, and D. D is 1 in both of them. So this is the answer. Okay? You can double check that. Right. Another question, number 4. Okay? Of multiplexers. But this case, we're using, asking for code in VHDL to implement that. And then we have 4 different expressions. And they're asking that which of the following VHDL statements models the 4-to-1 multiplexer given in the figure above. We look at the first one. The first expression say not A and not B and I0. That's exactly right for a multiplexer. That will be the function. That's the selection of the first input, input I0. The same thing for I1, which is not A, and B, that will be 0, 1, and then this is the selection of the input. So this is correct. How about this? Well, if you look in here, we're using a select statement. And with that, also, we're using this appending tool or symbol in which what you do is put these two things together. So A and then ampersand B means that the two things are allocated, one adjacent to the other. All right, this is append in this case. So we're using A and B, right? And A and B are supposed to be either 0 or 1 each one. So, for instance, in this case, we're looking into A and ampersand B could be 0, 0, 0, 1, 1, 0, 1, 1. And then depending on all these possible values, that are the only possible combinations, we have I0, I1, I2, and I3. So this is true. If you look into the third one, or C, that's pretty much the same thing. Okay? We're not using a select, but when it's like a if else type of statement that we have in VHDL. And similar, the D, the fourth one, is pretty much a variation of that. If you pay attention to this, you will realize that it's exactly the same thing. So I0 when both A and B are 0, I1 when I have 0, A0 and B1, and so on and so forth. So all the answer here is that all of above statements correspond to the 4-to-1 multiplexer. Okay, question number 5. Question number 5 is another multiplexer that implements a 4-to-1 function. Okay, for variable function rather. So careful with this case. One of the things that you need to observe is that we have the direction of these variables here, or the gates, are not the A, B, and C that we've been using, but they are reversed. So we need to, if that's the case, this would be the highest, most representative variable. This is the second one and third one, and this is the last one. Okay, from the most significant here, D, to the least significant, that is A. So the idea is that in order to maintain the same order of the mean terms, then we are supposed to do the reverse, or the change in the variables in the K-map. Okay, so we do exactly the same analysis. We have those rectangles correspond, in this case, for instance, I put a D equals 0, Z0, V0. Okay, D0, Z0, V0. What do we get? Well, we get this. We get this input, and it is 0. Doesn't matter which value of A here. A is going to be the variable that's called here. Same thing with the next one, with the 1, which is this rectangle right here. Remember this rectangle D0, C0, B1. And in both cases, disregard of the value of A is 0. The same thing now with the BCC here. We have exactly the same situation, but these two are 1. But let's see what happens here in number 2, in which we are tied to a variable A. H could be, of course, 0 or 1. So in this case, let's see what happened with the 2, which is 0, 1, 0. That will correspond to this number 2 port. So it's A that is in here. Therefore, if you look here, this variable here, the right variable here, corresponds to A, A0, A1. And this is what we get here. And that will be exactly what happens in the number 7, okay, that we have actually in here. You have to be careful because this is reverse. For A is in the upper side of the sector, and the 0 is in the lower. All right, so if you look into each one of these, we are asked, not directly, but this is at the other point, you see that all answers are given in not a sum of product or mean term, but we are given in terms of product of sums. So that means that we need to work with zeros. So we have one product here. It's a product of sum here. Okay, that's a 0, 0, 0, 0, and that corresponds to A, or in this case we need to put it in the same order, B or A. So B or A have to be there. So there's a B or A here, and well, I don't see any B or A here as well, and not in the other one. And then we have another implicate of 4 here that will correspond to D naught B. That will be D naught B is here as well. Then we have another one of 4, this vertical here, that will correspond to D or C, right? D or C is here. And the last one will be this here, that is 2. We can pair this only with this one. That will be D naught, C naught, A. D naught or C naught or A. So this is the answer. Okay, so careful with this, with the product of sum. It's not that hard. Okay, let's see what happens in question 6. Question 6, we have something different from multiplexer. We still have multiplexer. It's 2 to 1, but we add some stuff here in the boards. Okay, so see that in this case, by the way, we assume that we don't have anything here, and when the selector is given at some point in the multiplexer, the side that is shorter, closer to this selector, is usually the corresponding to I0, and this is to I1. Okay, so let's see the same trick here. So get the K-map or the truth table for that particular figure or circuit. We start with W0. W0 makes this upper side the input. So this AND with these two inputs. So it's clear to see that this branch here is going to be, because it's an AND, it's going to be 0 with the exception with this is a 1 and this is a 1, and that would be W2 0, right? And no, sorry, yes, W2 0 and W3 0. So both zeros is the only chance in which this is going to be 1 for the upper side, and this is the case. Okay, so see, the rest is not. And the same thing with the lower, which corresponds to when W1 is 1. And this is different because it's an OR, so we have situations, for instance, or could be, in this case, if W2 is 1, then we have this 1 here. If W3 is 0, then we also have that. So we can then complete this side to here, okay? And looking into that, we have 0, the mean term 0, the mean term 5, okay? Am I right? 0, 1, 2, 3, 4, I'm sorry. I didn't check the answer here for that. Okay. But this is 0, 1, 2, 3, 4, 5, 6, and 7. So let's see in terms of the max term. So we have let's see, we have 1, okay, 1, 2, 3, 5. This is the answer, okay? And we need to check if this also gives any chance to be even a 0. No, apparently not. But as I remember, this is the answer. Well, you can double check that. Right. Question 7 asks for what exactly is this circuit? What we implemented? Well, if you look into that, probably you have seen in the books that this is a MUX. So indeed, you have 3 selectors. The only difference of what we have done so far is that not use the enable, that basically allows to have here outputs. And if you look into how these are set, if for instance you have, let's suppose that you want to have the 0, 0, 0 here, that would be the I0. Okay, so if you have 0, 0, 0, then this side here of after the inverter is going to be 1. Therefore, all these lines are 1. Okay, and the same thing with the S1 and with the S2. So if you look into that, then you will see that only this and here is the one that is selected. Okay, and similar you do for the rest of the circuit. For instance, in the other stream we have 1, 1, 1, and then you will see that the only one that is selected is the 7. Okay, so this is actually it's a 8-to-1 multiplexer. Okay, all right. Question 8, I'm sorry. Question is a surprise. It's another multiplexer. This is the multiplexer, and we're giving several options for the function, for variable function that it works. So the very same approach. You throw the K-map with all the possible sections for that. The only thing is that if you look into here, okay, for instance, here we have 0 is 1, therefore we have, this is the 0, 0, 0, 0, 0, 0, then is, no matter what, is going to be 1. We have here D, so we have the 1 in the 0 here, and so on and so forth. So the approach to that is that if you look into the K-map, we don't have any two variable group. So you need to check, because there are many different ways to cover. Okay, if in fact, if you look carefully to this K-map, we have only one essential prime implicate, which is this one here, the, composed by B naught, C, and D. This is the one that cannot be substituted for anything else. So you have to be there. So taking that into consideration, then you can actually play with many of those choices in covering different ways. So I use that, so you may have different ones, and I start looking to different options. So this is that mandatory, probably. This is kind of obvious. Nevertheless, I can use, for instance, this to cover these two like this, and this to this also with one on here. Okay, but as I said, there are many choices. So the problem with this is that you have to look into here and see which one are the one that are covering. Okay, so for instance, in this case, there's no chance to be this. Here we have one, for instance, which is the 4 literal, and we don't have any one here like that. But if you look into that, well, and start checking, this, the second one, contains one path. In this case, this literal, this one of these two that you can choose, and one of these two, which is I think it's A naught BC, and the other one is the one that is BC. I think it's BCD naught. Okay, the rest are okay. Okay, so check that, and it's not that complicated. Okay, question 9. What do you think is the question 9 about? Another multiplexer. Okay, in this case we have a multiplexer that generates a function that probably you already know. I'm doing this because if you look into the options for the answers, we have pretty much this is a circuit, arithmetic circuit that provides an arithmetic function, either full subtractor, full adder, carry comparator, whatever that is, or none of the above. Even the carry in A, B, and then the sum, the carry out. I mean, it may give some either hints or simply something wrong. Okay, so the idea is here we're gonna do the complete truth table, and the way we work with that is exactly the same thing. Okay, so you simply plug number combination here. We only have H because this is a 3 variable, 2 output functions, and then we simply generate that, and this is what we have. Okay, so for instance, you put 0, 0, 0 here, and then you know that if we have 0 here, we're going to have a 0 in this case, and depending on what we have here, we're going to be using the 0 or the 1. So because we have 0 and 0, the XOR output here is going to be 0. So we have 0 here, so we're looking into that. So this is a 0, the carry out is a 0, and the sum is 0. And then you do exactly with the same thing. So if you look into that, this is a full adder. Okay, that's something that we know from CET3198. Okay, so full adder. Let's see with next question. What do you think is the next question about? It's not multiplexer. It's the cousin of the multiplexer is the decoder. And then we have done a lot of examples with this. So see that we have a 4 to 1 line decoder. That means that we have 4 inputs, and then we have all 10 mean term inverted. The output, you see, it's a bubble. That means that those are the mean terms are inverted. So in this case, for instance, if I put something in here, connect something, that will be the mean term 0, right? But inverted. That would be A0, B0, C0, D0 inverted. Okay? So, the useful thing of this 4 to 10 line decoder is with the NAND gates. So see that we have M1 not going in, M2 not going in, and M4 not going in. When we go to a NAND gate, this is exactly as if I eliminating the inversion here, and then this is converted into an OR. So this is the mean term expression, and it's given in 1, 2, 4 in this case, which is this, and the other one is 4, 7, and 9. So this is the answer, the option 1. I think we have worked that before, right? Okay. Option 11, question 11, is a code in VHDL, okay? And that's something that by now we should know exactly what is that. If you remember the hex display that we have in the boards, basically follow this, okay? So we have a select with 4 input B, C, and D. B, C, and D select, okay? So we have 3 inputs here. So we have an output of from 1 to 7, okay? 7 different lines, the output. That is basically, if you look into what exactly is that we're doing the hex code, the hex display, okay? So, we have, in this case, it's a BCD to 7 segment decoder, okay? Because actually what we're having here are codes in BCD, okay? Okay, question 12. We go back to multiplexers, and again the same thing. In this case, I also work with the truth table, because we are generating expressions that are easily grabbed from the truth table. Okay, so all we need to do is just get for W2, again, we'll assume that W2 0 is this port on the upper side, and W2 1 is this. And then we start looking one by one. If W2 is 0, then if we're selecting this, so if W3 is 0, we have a 1, but if W3 is 1, this is 0. Okay, so this is pretty much what the truth table looks. Okay, and in this case we have this term, mean term, is W1 not, W2 not, W3 not, this term that is here and here, and this one is W1, W2 not, W3 not is here, and the last two, so sorry, W1, W2 not, okay, that's here, and then we have W1, W2, W1, W2, W3 not. Okay, that's the other one, and this is W1, W2, W3, which is this. So this is the answer, the B. Okay, very easy. Okay, question 13. We have something that we're supposed to know, right? From what we did in the lab when we work with the multiplier. Okay, so if you look into here, we have a 16 bits one input, and the other is 16 bits. Okay, so that means that in order to get sufficient digits to express the product has to be the sum of these two. Okay, that's something that we learn in the lab. So we need to have 32 bits in this case. Okay, 16 and 16, 32. And the reason for that is you look into what is the maximum size of a number of 16 bits. Okay, times another of 16 bits, and then you find, well, the maximum number here is 2 to the 16 times another of 2 to the 16. That would be 2 to the 32 if you add these two powers of 2. Okay, so the answer is 32. Question 14. Okay, guess what? It's another multiplexer. In this case, we have, it's a very interesting problem because we have the following. We have the inputs of the 4 to 1 mux are gates. So we have two inputs here that goes through the gates, and then they generate a 4 variable function using this trick. So we have supposedly gates of 2 inputs here, 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 and here, and we need to guess what are the gates that we're using there. Okay, so the only thing that you need to look into is see that we have all the 4 functions, okay, that will depend on C and D. So if this is C and D in the K-map, if you look into what this represents, for instance, C0, D0, C0, D0 is this. Okay, so that, if you look here, it will tell for what values of A and B we have 1s or 0s. Therefore, because it's a 2 input variable, 2 input gate, so we have only 4 possibilities. Those are the truth tables for each one of the gates. So what we need to do is look into the truth tables of each one. For instance, in this case, we have that we have a 1, right, when input A and B are different. What is that? Well, this is an XOR. Okay, this is the truth table for an XOR. This is a truth table for a function that has a 1 only when we have A1, B1. What kind of gate is that? And then F3, okay, this one is a gate in which you only have a 1 when the inputs are the same and are 0. What are they? Well, you should know. Okay, it should be an OR gate. Okay, and the same thing with this, the F2, in which the only chance in which you have a 0 is when you have 1, 1. What is that? That's an AND gate. Okay, so you have a 1 if any of these 2 inputs are 0, but 0 if both are 1. Okay? So you select and then you check that. Double check that because okay, in the last question is a question that pretty much review the concatenation property in VHDL. Okay? So we have variables A and B. A is 101, is 3 bits, and B is also 3 bits, 011. And then we want to know this. What is the result of this? This is a logic expression. So your answer should be that's true or it's false. Okay, so all we need to do is just say, for instance, this side of the of this, that would be a test, like a comparison. We have A and B. This is what corresponds to A and B. This would be A 101 and B 011 put together according to this. And then when you do not, you simply flip the flip the bits like a one's complement. Okay, that would be the not, the logic not in this case. And the same thing we do with B and A. Okay. And then we negate that because we need to compare the negation of A concatenated with B, and this is it. And then we use then this operation in which we get not B concatenated with A, okay? B concatenated with A is this, and A concatenated with A and not. So we have these two results. We do the AND between these two things, okay? This AND, and the AND is 0, 0, 0, 1. In this case, when we compare this versus this, you see that this is greater, no smaller. So the answer is false. Okay, so I hope that you clarify any ways the answers from the homework. I'm open to any questions, so let me know if you have any questions or anything regarding this homework. Well, by the way, the exam is going to be posted at 12 to 12. Well, it's in the program there. Okay, so if you have any questions, I'll be more than glad, even during the exam, to clarify any situation. Okay. Well, thank you so much.